Pluto is quite far away from the Sun, so the sunlight there is multiple times fainter than it is here on Earth. As a result, temperatures can drop to around -230 degrees Celsius during the evening. However, under certain conditions, temperatures might spike to as high as 170 degrees Celsius. Its environment is extremely dubious, welcoming inquisitive personalities to investigate beyond the natural domains of our solar system. Imagine if I told you that Pluto, the distant and mysterious dwarf planet, is finally taking its infinite action, possibly colliding with none other than Neptune, the ice giant. Pluto's insubordinate nature has been clear from the start. It's a maverick on the edges of our celestial region. Its orbit, daringly running into that of another planet, challenges the conventional standards of planetary conduct. Astrophysicists like Neil deGrasse Tyson and Michio Kaku have voiced raised concerns about the implications of such a potential collision. A lingering question hangs in the cosmic balance: will these divine giants engage in a catastrophic clash? Could the union of their paths spell unexpected ramifications for our beloved Earth? Today, we embark on an immense journey filled with uncertainty. While answers to these celestial questions may elude us, the prospect of a monumental impact serves as a stark reminder that the universe is a stage for both spectacular events and daunting mysteries. Join us as we delve into the secrets surrounding Pluto and Neptune, contemplating the potential outcomes of a cosmic conflict that could reshape the intricate balance of our solar system. The stage is set, and the unfolding drama beckons us to witness the enigmatic dance of the planets. Among the many potential cosmic catastrophes, the universe harbors a variety of puzzles, including the intricate riddle known as the three-body problem. Researchers also anticipate other possible disturbances within this cosmic theater. Although a planet colliding with another in space is extremely unlikely, it is not entirely out of the question. Gravitational interactions, as described by the three-body problem, are one of the forces that influence planetary orbits. An example of a system where gravitational forces create an intermittent pattern known as orbital resonances is TRAPPIST-1, which has 7 planets about the size of Earth. Over time, these patterns could destabilize planetary orbits, increasing the likelihood of impacts. This scenario does not exclude crashes entirely. In dense systems like TRAPPIST-1, where planets influence one another's courses, researchers constantly monitor these dynamics to better understand how planets traverse space. Another obscure yet fascinating concept involves rogue planets, which drift aimlessly through space rather than orbiting a star. The ejection of planets from star systems can occur due to gravitational interactions or other cosmic phenomena, such as the close approach of another star or dynamic instability in multi-planet systems. Over time, these wandering planets can travel vast distances, potentially even reaching areas far from where they originated. It is conceivable that they could encounter other star systems on their solitary journeys. However, the probability of a rogue planet colliding head-on with another planet is quite low, considering the vast emptiness of space. The scarcity of planets in open space and the enormity of interstellar distances work together to deter frequent collisions. While it is now highly improbable that 2 rogue planets will collide, the frequency of rogue planets is significantly lower than that of stars and planets in stable orbits. The star systems involved can become chaotic during cosmic mergers, but it remains highly unlikely that planets will impact one another directly due to the immense interstellar distances. The orbits of stars and planets within emerging systems are finely balanced by strong gravitational forces. A planet may become a rogue world, liberated from any star, when such disturbances push it into the cold, dark depths of intergalactic space. Conversely, planets could be ejected from their orbits, collide with one another, or even influence their host stars due to these gravitational disruptions. When gas and dust are compressed under extremely high pressure, gravitational interactions can lead to the formation of new celestial bodies or even trigger the birth of stars within our solar system. The late heavy bombardment suggests that around 4 billion years ago, there was a period of increased collisions involving comets and asteroids. This surge in activity is believed to have resulted from gravitational disturbances caused by the outer planets. During this tumultuous period, gas giants like Jupiter and Saturn were migrating, disrupting the orbits of various smaller bodies in the Kuiper belt and asteroid belt. As a result, these smaller objects were thrown into erratic trajectories, with many entering the inner solar system. This influx led to a significant increase in impacts on terrestrial planets, including Earth. While these impacts did not involve direct collisions between planets, they illustrate how gravitational interactions can cause substantial shifts in the paths of celestial bodies. This bombardment is thought to have played a crucial role in shaping the surfaces and geological histories of the planets in our solar system. Additionally, it may have contributed to the delivery of water and organic materials to Earth, influencing the evolution of our planet over a long period. As stars undergo changes in mass, the orbits of the planets around them can also be affected. This is especially noticeable in systems where stars are at the end of their life cycle. As a star ages and consumes its nuclear fuel, it often undergoes significant mass changes, particularly during stages like the red giant phase or when it ejects material in a planetary nebula. These variations in stellar mass can substantially influence the gravitational balance of the system, causing the orbits of nearby planets to either shift outward or become more compact. This phenomenon is more likely to occur in multi-star systems, where complex gravitational interactions can lead to unstable orbits. In such systems, the gravitational forces from multiple stars can act erratically, exacerbating orbital shifts and increasing the likelihood of orbit crossings. This could result in scenarios where planets get captured by another star, collide with other celestial bodies, or even get ejected into interstellar space. Pluto's unique orbit, initially recognized as a clear member of the planetary family, underwent a reclassification to dwarf planet due to its distinct characteristics. The astronomical community remains captivated by Pluto, finding it intriguing despite this change. Concerns about Pluto's proximity to Neptune have been raised by prominent researchers like Neil deGrasse Tyson and Michio Kaku. They warn of a grave danger to Earth, highlighting the unusual nature of Pluto and the uniqueness of its orbit around the Sun. Pluto has not completed a full orbit since its revelation in 1930, and its orbital period spans approximately 248 years. The fact that it deviates significantly from the generally circular orbits of the larger planets makes its path incredibly eccentric. Pluto also has a more inclined orbit than other planets, with an inclination of about 17 degrees to the ecliptic plane. An interesting aspect of Pluto's orbital pattern is its interaction with Neptune's orbit. For roughly 20 years during each of Pluto's orbits, it comes closer to the Sun than Neptune, challenging assumptions based on their respective positions in the solar system. This leads to the question, why hasn't a collision between Pluto and Neptune occurred? The explanation lies in the gravitational effects exerted by other planets. The evaluation of Pluto's orbit began shortly after its discovery, presenting a complex challenge for astronomers. Unlike most planets, whose orbits remain relatively aligned with the ecliptic plane, Pluto's unique characteristics include a steep inclination and a highly eccentric shape. The mystery deepens with the realization that Pluto's orbit crosses that of Neptune. The three-body problem, which involves understanding the gravitational interactions between Pluto, Neptune, and the Sun, highlights the complexity of celestial mechanics. Predicting their trajectories from their initial positions and the effects of gravity on each other is challenging. Key terms that help to address this cosmic puzzle include azimuth libration, scope libration, and the Kozai mechanism. According to astrophysicists, azimuth libration is crucial because it helps maintain the stability of planetary orbits. When Pluto crosses Neptune's orbit, it is positioned approximately 90 degrees away from Neptune, a critical distance that prevents collisions. Scope libration, which refers to the vertical movement of a celestial body in its orbit, ensures that when Pluto approaches Neptune or other giant planets, it is positioned significantly above their orbital plane, providing an additional layer of protection against collisions. A significant factor in understanding celestial movement is the Kozai mechanism, named after three researchers who explored the gravitational interactions among three celestial objects, specifically Pluto, Neptune, and the Sun. The Kozai mechanism explains why Pluto's orbit around the Sun appears irregular, yet remains stable over long time frames despite the apparent chaos in space. These factors collectively stabilize Pluto's orbit, preventing impacts with Neptune and deviations from its path. The three-body problem aids in understanding how the gravitational influences of these celestial objects affect their trajectories. This knowledge contributes to our understanding of Pluto, our solar system, and distant celestial bodies. Mathematical simulations in the late 1980s revealed that despite its stable properties, Pluto's orbit is indeed chaotic, with minor initial deviations leading to significant changes over millennia. Nonetheless, Pluto's unique orbit demonstrates remarkable stability over extensive periods, effectively mitigating potential disorder. Recent observational studies have deepened our understanding of the complex dynamics involving massive planets like Neptune, Jupiter, and Saturn, which significantly influence Pluto's trajectory around the Sun. Neptune's gravitational impact completes 3 orbits for every 2 of Pluto, contributing to the overall stability of Pluto's orbital path. Jupiter's gravity also plays a role, albeit to a lesser extent than Saturn's. Taken as a whole, these observations illustrate that Pluto is in secure and consistent motion across space over billions of years, safeguarded by the combined gravitational effects of Jupiter, Saturn, and Neptune. These dynamics are essential for preventing disruptions in the solar system's structure. Without these stabilizing interactions, the solar system would be more chaotic and unpredictable, increasing the likelihood of collisions and deviations from stable orbits, which could have significant ramifications for other celestial bodies. Understanding Pluto's orbit is vital in light of theories regarding a potential collision between Pluto and Neptune. With this knowledge, the ever-changing solar system can be better understood. The case of Pluto exemplifies how the intricate relationship between orbital mechanics and gravitational forces can result in seemingly unstable orbits achieving long-term stability. To comprehend our position in the universe, it is crucial to continuously observe and investigate these celestial events. Space exploration often uncovers the erratic behavior of celestial bodies, with Pluto's orbit serving as a classic example of this unpredictability. Pluto's case provides a striking illustration of the potential for orbital chaos, showing how the trajectory of a celestial body is deeply influenced by its initial conditions. Minor changes in the dwarf planet's position or velocity can significantly affect its orbital path. Over time, researchers' understanding of Pluto's motion in space has largely been informed by simulations designed to replicate the gravitational interactions between Pluto and other planetary bodies like Neptune. These simulations utilize complex mathematical models that allow astronomers to visualize how tiny variations can profoundly influence Pluto's trajectory. By adjusting these models, researchers discover that while Pluto's orbit can still be somewhat irregular with eccentric orbits, is challenging. The intrinsic unpredictability of these systems complicates long-term forecasts. Mathematical simulations help us understand and anticipate the future paths of celestial bodies, but they also reveal the limitations of our predictive capabilities. These models heavily depend on accurate initial conditions and replicate complex interactions. Even small errors can lead to vastly different outcomes, making precise predictions difficult. The turbulent nature of celestial orbits like Pluto's reminds us of the ever-changing universe. While we have made strides in understanding space, Pluto's case underscores our ongoing limited knowledge. Understanding the gravitational influences of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system, illustrating how each planet's existence and position can affect the stability and trajectory of other bodies within the system. Concerns about a possible collision between Pluto and Neptune highlight the importance of comprehending Pluto's orbit and the dynamic nature of the solar system. Neil deGrasse Tyson, a famous astrophysicist critical in advocating stargazing, offers an unmistakable point of view on the puzzlers inside our planetary group, especially zeroing in on Pluto. Tyson, remarkable for renaming Pluto from an undeniable planet to a dwarf planet, shares sagacious reflections on the evolving nature of our understanding of celestial mechanics and humanity's enduring interest in the neglected domains of space. Rather than viewing Pluto's renaming as a downgrade, Tyson considers it a significant change that aligns with the expanding knowledge about the various objects orbiting the Sun. His approach to celestial mechanics is rooted in continuous learning and transformation. Tyson sees the complexities of orbits exemplified by Pluto's unique path as a constant reminder of the boundlessness of information ready to be uncovered in space. He states that the emergence of these infinite questions is the main driving force behind the enthralling nature of astrophysics. Tyson also recognizes the essential role of space-related events and discoveries in shaping public interest in space science. He views occurrences like Pluto's renaming and its eccentric orbit as opportunities to ignite the public's imagination and curiosity about the universe. By delving into the dynamic and sometimes nonsensical aspects of celestial mechanics, Tyson opens a doorway for the general public to marvel at the wonders and mysteries of the cosmos. Working alongside other researchers, Tyson has actively informed the public about the potential risks of Pluto's erratic path. After studying Pluto extensively, he has raised concerns that the three-body problem could pose a real threat, suggesting that a collision with Neptune is long overdue. He emphasizes how such a crash could disrupt the equilibrium of the universe and lead to catastrophic results, extending even to Earth. A collision between Pluto and Neptune would be a rare and disastrous event in our solar system, releasing a massive amount of energy and potentially breaking Pluto apart due to its smaller size and icy composition. Debris from the impact could scatter across the solar system, posing risks for other planets and their moons. For Neptune, such an impact could even alter its atmosphere and orbit, depending on the specifics of the collision. Michio Kaku, a recognized theoretical physicist renowned for his contributions to string theory and science advocacy, brings a distinctive perspective to this unfolding situation. His insights into the future of space exploration and the intricate connection between celestial mechanics and theoretical physics provide significant reflections on phenomena such as Pluto's orbit. Kaku sees the study of Pluto and its trajectory as a window into the broader realms of space exploration. According to him, unraveling the complex gravitational interactions and orbital characteristics of celestial bodies represented by Pluto offers invaluable insights for upcoming space missions. This acquired knowledge becomes instrumental in navigating the solar system, effectively predicting potential dangers and strategically planning missions to the outer reaches of our solar neighborhood and beyond. Kaku emphasizes that the lessons gleaned from studying Pluto's orbit can serve as a framework for approaching and understanding other distant celestial bodies. He consistently highlights the profound interconnection between celestial mechanics and theoretical physics, arguing that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated events but intricately linked to fundamental principles of physics. Kaku's interests in theoretical physics, particularly in the domain of string theory, aim to comprehend these principles at the most fundamental level. He posits that probing into the intricacies of celestial mechanics exemplified by Pluto's orbit has the potential to reveal insights into the basic laws governing the universe. Like Tyson, Kaku explores the cosmic implications of a potential impact, seamlessly weaving it into his broader theories about the universe. If Pluto and Neptune were to collide, it would be a momentous event in astronomy, offering a remarkable observational opportunity that could contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, attempts to describe the fundamental forces and matter in the universe. A collision of such magnitude in the solar system could generate extreme states of energy and gravity, providing insights into the behavior of fundamental particles and forces under extraordinary conditions, a key focus of string theory. Furthermore, the gravitational waves produced by the impact could yield valuable data for testing predictions of string theory related to gravity and spacetime. While the immediate effect on Earth would be negligible due to our distance from the outer solar system, the scientific ramifications of such an event could be significant, potentially enhancing our understanding of the essential nature of the universe as described by string theory and other areas of theoretical physics. Ultimately, Pluto's orbit serves as an exceptional illustration of celestial mechanics, showcasing both stability and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, especially Neptune, highlight the intricate and dynamic nature of space. In all these imagined scenarios, the genuine likelihood of a planetary collision remains extremely remote. The vastness of space combined with the relatively small size of celestial bodies makes direct collisions rare occurrences. Nevertheless, these speculative situations captivate the attention of astronomers and astrophysicists, serving as significant windows into the dynamics of planetary systems and the evolutionary tapestry of the cosmos. The ongoing study of Pluto's orbit represents a continuous quest for knowledge within the realm of space exploration, as illustrated by Tyson and Kaku. Each discovery brings us closer to unraveling the complex fabric of our universe. It is a journey that not only challenges our current understandings but also expands our horizons, laying the groundwork for future generations of explorers and scientists. The allure of the universe, with its secrets and possibilities, compels us forward on a path of discovery and understanding. As we conclude our cosmic journey into the potential collision between Pluto and Neptune, it is essential to recognize that this celestial rendezvous remains a distant possibility. Yet, the mere idea of such an event reveals the inherently unpredictable nature of space. Our exploration has taken us from the specific orbits of distant planets to the monumental interplay of worlds colliding. As we continue to delve into the universe, who knows what other surprises await us?